Then OBS start record.
Kita dah habis dah prototype 1, jadi kita
this is the audio one. So I have to open the face-to-face slide, which is this one. That one's wrong, was a wrong slide. Okay, so I hope that all of you already received this slide that I have given to you guys in the WhatsApp group. Okay, so for today's session, we will cover on the topic 5, which is prototyping part 2. So these are the objectives of the prototyping part 2 that we are going to achieve about 4 objectives in this study. All right. So at the end of this chapter or topic, I hope that the students will be able to understand about the assembly of the printed circuit board, okay, which is about PCB assembly technique. I'm going to pick up my pointer. Where is my pointer? I couldn't access the pointer from here. No problem. Okay, just start. All right. Second one, design and fabricate a cabinet. Okay, which is more to the mechanical works, which is, for example, we are going to use the sheet metal to do the design of the cabinet, which is our enclosure for the circuit. Okay, for this one, like some of the works related to making holes, do the bending of the sheet metal, do the cuttings of the sheet metal, and some painting, which is the finishing work to our cabinet. All right. Number 3 is to complete the final wiring, which is the student should be able to understand on how to do the wirings of PCB. For example, we have the PCB. Some of the components is placed on the PCB, but some of the component is outside of the PCB that we have to do the wirings. For example, as you can see in this figure, we have some things like computer system, for example. Some components like fan, DC fan here need to be wired from the PCB, okay, from the motherboard, for example. Okay, some of the component like CD or DVD also need to do wirings. Okay, some component like USB user interface based component like switch, okay, the display, for example, we need to do the wiring to the PCB. Okay, number 4, assemble all elements into a complete prototype project, which is how does our project looks like from outside, which is the final prototype that we have. After we complete do all of the wirings, then next is to finalize our prototype. So this one is more to the finishing lah, in terms of we would like to do some paintings or vinyl coating finish. Right. So next, these are the topics of prototyping 2. These are the topics of the prototyping 2, which is we will cover about 4 topics, 4 subtopics or sections, which is 5.5, 5.1. I'll be talking about PCB assembly, which is still related to PCB, this one. So I can get my laser pointer. All right. So 5.1 is still about PCB, which is how do we place the component on the PCB and do the soldering of that component. For 5.2, 5.3, and 5.4, please unmute, please mute. Make sure to mute your mic. Siapa ni? Amira. Maybe Amira is having trouble with his with her connection, right? I hope you guys doing well. Maybe some of you might be sleep. Is that all right? Okay, so we continue. For Unit 5, we have 4 sections, 4 subtopics, which is 5.1, we will cover about PCB assembly, which is about the component assembly on the PCB and how do we do the soldering process of the component on the PCB. And then 5.2, 5.3, and 5.4 is about the cabinet. Okay, how do we design the enclosure for our circuit? Okay, so this one cabinet is more to some things like sounds like mechanical based work. Okay, PCB is still electrical based work. All right. Okay, so to achieve all of the objective that we set in this topic, which is 4 objectives, so we need to refer to our previous session, which is in topic 2, we have discussed about 10 sets of drawing. But in this topic, there's a few drawings that will be used to cover all of the objective, which is we are going to I'm going to talk about PCB assembly, which is component assembly on the PCB, so that we can refer to PCB assembly drawings. And then sheet metal drawing is another drawing that is used for designing our enclosure or cabinet. And then wiring drawing, which is related to wires that is connected from PCB to the outside of the outside component or the component that is outside of the PCB. Okay. And then number 4, packaging drawing, which is the final packaging plan of our project or prototype. So we will consider all of these 4 drawing throughout this letter and throughout the slides. Huh? Okay, the first one, which is about PCB assembly drawings. So for the PCB assembly drawings, basically we will need at least, it should contain at least 3 items. The first one is related to view of the component showing their layout, which is, as you can see in this example, we can see that the component is clearly stated here. For example, the component layout for R1 is the resistor. Okay, component layout for C4, for example, here is for the capacitor. And other components like transformer, silicon control rectifier, SCR, and also F, which is, I think this is a fuse, right? So basically, we will see on the board here, on the drawing here, some layout of the component. Number 2, it's about notes. We will write some notes. For example, as you can see in this example drawing, here we have some notes written on this drawing. To, for example, number 1 is C schematic drawing number 4A. Okay, in this PCB assembly drawing, what we are going to do with the component, basically, we also need to refer to schematic drawing. For example, we are referring to schematic drawing of 4A to do this assembly drawing. It's to do this assembly of the component based on this assembly drawings. So basically, there are some notes that provide us some guidelines when we do the component assembly on the PCB board. Number 3 is part list. Okay, the list of parts that we are going to use during the PCB assembly process. As you can see, this is an example of the table that shows the part list. All of the components, not only the component that is placed on that PCB, but also the components which is used as an auxiliary component or non-component parts also listed here. For example, for SCR, not only one SCR is mentioned here, which is number 15. It is mentioned that SCR1 SCR2 and SCR3, and then the model of the SCR, which is C106B1, and how much SCR that we are going to use in this PCB assembly. It's stated here three SCR is going to be used. Okay, so this is basically the table that shows the part list. Okay, this is the part list. And then there are some other things that we will need to consider for the PCB assembly drawings in terms of the drawing scale, which is the size of the scale in comparison to the actual size of the component. Basically, for the scale, we'll make sure that the drawings is the same scale to the PCB assembly drawing is the same scale to the PCB artwork. Okay, so we have the PCB artwork drawing that is basically represents the back side of the PCB, which shows the traces and pads, right? But for the PCB assembly drawing, which is the components drawing, component layout here, which is referring to the component side of the PCB. So basically, the size of the PCB assembly drawing is the same size to the PCB artwork drawing, which is, for example, most of the project, the drawing will be the same size to the component size, which is 1:1. Okay, which is exactly the actual size of the component. Okay, and then the orientation and wire jumpers also should be stated on the PCB drawings. Orientation means we want to make sure that in terms of polarity of the component, so we should know about which terminal represent the positive terminal, which terminal represent the grounding or negative terminal. So we want to make sure that we do the assembly of the component on the board. We are not making mistake in terms of rotation of the component. If we mistakenly put the component when we supply the voltage to the board, what happen is the component will burn out. So it is easy for the component to be broken. Then so these are some of the characteristics of the PCB assembly drawings. For example, the first one, in terms of scale, okay? So the PCB assembly drawing is usually drawn to the same scale as the artwork. So before this, we have the PCB artwork, right? So basically, the PCB assembly drawings is the same scale, which is 1:1, okay? Which is actual size of the component, actual size of the PCB artwork, which is, for example, we have the traces, okay? So for the PCB assembly drawings also will have the same size. Okay, the other one is view, in terms of view. So for the PCB assembly drawings, it is viewed from the component side. For the PCB artwork, it is actually the back side of the PCB, okay, which is the traces side. But for the PCB assembly drawing, the view is from the component side, which is, I think it is easier for us to say that it is from the top side, okay, the top side of the PCB. The bottom side is traces, which is more to the PCB artwork, okay. The top side is component side, which is the PCB assembly, all right. So, okay, so that one is in terms of view of the component. And also, we need also to consider the side view. So in the PCB assembly drawings, there is also the side view of the PCB. Like in this example, as you can see, we have this PCB, which is the top view, which is the component side view of the PCB. Okay, and the other one here is the side view. So this is the PCB and the height of the components. Which component has the highest height, the highest the top of the component, for example, should be less than 7/8 inch here, meaning that we should know the height of the component, the highest component, to make sure that when we design the enclosure, we don't want the component to touch the body of the enclosure or cabinet. Okay, so that is about view of the component, view of the PCB assembly drawings, right? So that shows the component from the component side and also the side view of the drawings. And then component identification. So basically for the component identification, as you can see on the drawing, we will know that, for example, this one is the resistor, this one is capacitor, which is stated clearly in this drawing. The symbol, okay, the symbol of the component, to show us to make sure that we can identify the component easily, right? Okay, and then component orientation. So this is basically related to the polarity of the components. Some components don't have polarity, like the resistor don't have polarity. There is no plus minus for the resistor. So you can freely place the resistor either without considering any without taking into account its polarity. Okay, but for other components like LED, for example, LED has the polarity plus minus, right? So you have to make sure that when you place the component on the PCB, it is placed in the right polarity. Okay, especially for the component which is easily to be broken, like IC. Okay, so some IC is I don't have IC. Some IC, it has many pins for the IC. Okay, for example, if I can show you from here, I'll just open my browser. Where is my browser? Close this. For example, 555 IC. For IC like this, for example, it has a pin dedicated to ground, and then pin dedicated to VCC, which is input. For example, 5 volt of input. Okay, so this is ground, which is negative terminal or zero voltage terminal. Okay, and then some pins for the input and output. So if you accidentally put this IC to different polarity, to reverse polarity, for example, it will easily burn out because we cannot connect grounding to positive terminal. Okay, so if we supply voltage to this grounding, it will burn this IC chip. Okay, then what else? Component orientation, and then jumper wires. So some PCB board has jumper wires that is normally represented as a straight lines. Then the jumper wires can be identified by using the symbol of J, which is J1, J2, J3, so and so on. Okay, and then non-component parts. Okay, for example, a resistor, capacitor, a diode, and some ICs, they are all the component, the electrical component, the electronics component. But there are also non-component parts. That is, that some of the non-component parts is used for heat dissipation, for heat sinks, for example, spacers, fasteners. Okay, so for the non-component part on the PCB assembly drawing, they are normally represented by balloon item numbers. As you can see, these balloon item numbers, for example, this is number 1. So this one could be the non-component. So this is also a non-component. For example, number 2 can be some spaces for this fuse. All right. Okay. So next is about part list. So for the PCB assembly drawing, it should has part list, which is a clear list of the components, which is in separate sheet like this. So this is an example of the part list in a separate sheet of the drawings. Okay. And then notes. Okay, as I think as it has already been explained before, which is something like this. We put some notes to guide us during the component assembly, right? Okay. And then a sort of things about some of the characteristics of the PCB assembly drawings. All right. So basically, in the PCB assembly drawings, it should have these components. For example, we have to make sure that the minimum criteria for our PCB assembly drawing should have some borders and title blocks, which is we have the title block, which okay. For example, the title for this drawing is PCB board assembly drawing, three channel organ, right? This is the title. So at least it should have a title, side view to show maximum height above the PCB surface, which is this one. This is the side view to show the maximum component from the surface of the PCB. Which component is has the height at this height, 7/8 inch of height. Then all component parts and list, all components and part, which is this one, the component list, and any notes, the notes that is specified on the PCB drawings, PCB assembly drawings, and also the part list. So at least it should have these 5 items on the PCB assembly drawings. So this is basically the drawing procedure that we have discussed this in our previous session, topic 2, which is about drawing. There are many items in drawing procedure, but at least for the PCB assembly drawing, it should have all of these 5 items. And then PCB assembly technique. So once we finish with the drawing, okay, PCB assembly drawings, now we are going to do the assembly process of the component, meaning that we want to do the soldering process of the component placement, component selection, component soldering, and so on. Okay. So before we do the assembly of the component, things that we should consider is about the component lead preparation. So some of the component, we call it as axial lead component, like resistor, and also the radial lead component, like the capacitor, okay, like the LED, for example, that is the radial lead component. Some solid state discrete component, like transistor, okay, and also the IC leads component. So we have different types of component leads. Okay, so for each type of component, like axial lead component, radial lead component, solid state discrete component, IC, so we have to consider the lead preparation. Okay, so this is about the lead preparation of the axial lead component. Axial lead component, for example, the resistor. So we want to make sure that we do the right thing, we do a correct way of preparing the resistor. For example, when we want to bend the resistor, we will bend it at the angle 90 degree using needle nose pliers, which is the long nose. The needle nose plier. The needle nose plier, which is this one. So this is the needle nose plier. We can use this to bend our component lead. For example, the resistor that is shown here. Okay, so we use the long nose or needle nose pliers to bend the lead of the resistor. And then when we bend it, we cannot bend it too close to the component body. For example, when we hold the resistor, make sure to leave some space from the body to bend before we bend it. Okay, we have to leave at least twice the lead diameter. For example, lead diameter is 1 millimeter. So at least 2 millimeter, we must spend some space before we bend it. Okay, because we don't want to bend too close to the component, too close to the resistor. Something like this, as you can see here, which is this one is the way how we bend the resistor, and one of the example that we can use to bend the resistor. These are some other types of axial lead component, which is this is an axial capacitor. The resistor is one of them. And then this could be some diode, all right? This is the axial lead component, which is this one is diode, okay? And second one is radial leads. Okay, the first one is axial lead. This one is radial leads. Radial leads, some things like this, which is like the capacitor here. As you can see, this is the type of radial leads component. Okay, so for radial lead component, there is no bending. There is no need to bend the lead of this capacitor, for example. So what we need to do is just to hold the component, and drop it straight onto the board. Okay, drop it straight onto the board, into the hole of the through hole. Okay, so some of the radial leads component, they have the kinkered pair of leads. Like as you can see in this example, this is the kinkered pair of leads, which is something like bending, a bit of bending here, which is this is outside, this is outside kink, to make sure that when we place the component, the component body will not be too close to the board. If the component has the kinkered pair of leads, which is we will leave some space at the bottom of the component to make sure some air, okay, some component like transistor, it should have some ventilation to make sure the component always cools down during operation. So we want to make sure there's some space leave under the component. Okay, so that is the purpose of the kinkered pair of leads, kinkered leads. So some components, like I told earlier, like transistor, the switching device, we should make some space under the component to make sure there is a cooling effects, which is when it is operating, it will release some heat. Okay, so it will release some heat. So to make sure that the heat is easily dissipated by the air. Okay, so we just leave it. For example, something like this, we leave some space under the component to make sure that it has some cooling effects to this component. Okay, some types of radial component, which is this is the ceramic capacitor, the electrolytic capacitor, and some other types of radial component. LED is also one of the types of radial component. And then component lead preparation for the solid state device. Component preparation, I lost my pointer again. Component preparation for the solid state device, okay, like IC. IC is one of the type of solid state device, and also the operational amplifiers, okay. Okay, so for this type of component like IC, sorry, solid state device like this one, right? So some of the solid state device, for example, silicon control rectifier, triac, and other solid state discrete component, like as you can see in this figure-based example at the bottom. Like this one is silicon control rectifier. Okay, so we want to make sure that we do not bend. Okay, we do not do bending of the lead of this component. Okay, because these components are delicate items which is easily to be broken. So we have to handle it securely to make sure that we don't spoil this component, right? Actually, we do not bend too close to the component body. We can bend it, but we do not bend too close to the component body. Like, as you can see in this example, the SCR here, there are some parts that will stop when we put this SCR onto the board, into the board, all right? It will stop at this point, okay? To make sure that the component body is not touching the PCB board. So next is IC. Similarly, for the solid state component, we don't want this IC to be very close, which is completely attached or completely touch the PCB. Okay, we want to leave some space under this IC, because inside this IC sometimes it has some switching component as well, and then it will heat up. Okay, to allow some ventilation, cooling effects to this component, we want to make sure that the body of the component like IC do not touch the PCB board. Okay, and here is some general guideline in component lead preparation. So basically, we will leave some space under the component. So some common component is mounted flush, which is the same level to the PCB. The component, basically, for example, the resistor. When we place the resistor, we'll make sure that it is touching, it will touch the PCB board. So the resistor have no problem, because it it is not switching device, it's just a passive device. So we can just place the resistor, flushing, okay? Same level to the PCB. But some other component which has the kinkered leads, we must make sure to allow some space under the component, okay? Some component will generate excessive heat, such as transistors, okay? So for the transistor also, we want to make sure that when we place the transistor, it is not too close to the PCB, to the surface of the PCB, right? So we will leave some space, which is, for example, in this case, we can leave some 0.4 cm from the body to the surface of the PCB. So a good spacer, is about a popsicle stick, which is the size of popsicle stick. Okay. So we want to leave some space under the component. A good spacing is about the size of popsicle stick lah, batang ice cream dia, right? Okay, and then component insertion and soldering. So before this, we have been discussing about preparing the leads of the component, right? But this one is more to the insertion of the component and do the soldering. Okay, before we do the soldering of the component, we do the insertion of the component. We want to make sure that our PCB is clean enough. Okay, so we have to clean the surface of the PCB to get rid of some oil, right? So to make sure that there is no something like particles like steel. For example, if we have some steel on our PCB, that steel might be short. That might be short, the traces. Okay, so we just use the paintbrush, for example, to get rid of the particles like steel. Okay, some protoboard like this. Some protoboard like this, when it is manufactured, basically there is some oily surface. We can feel like some things like oil on the surface. So when we do the soldering, it will not stick. We will not do the good joint because of the oil. So what we do is to clean it. For example, we can use the non-oil based steel wool and also non-abrasive cleanser to make sure that is all of the oil will be cleaned out from this surface of the PCB. Okay, and also our hand is also oily. Be sure that oil from your hand does not contaminate the solder pads. So solder pad is sensitive area because we will do the soldering on the solder pad. So if we touch it if we accidentally touch it with our hands, it will leave some oil on that solder pad, so that when we do the soldering, it will not stick properly, right? And then failure to take this simple step will prevent good solder joints from forming. Okay, for example, we will leave some wetting, not so good wetting action, because there are some oil on the surface of the PCB before we do the joining or the soldering of the component to the solder pads. Make sure that it is clean enough. Normal practice in our lab is basically we use some sandpaper. Use the sandpaper to rub it, to clean it, to make sure that protoboard is clean enough, which is shiny enough before we start our soldering process. Okay. So after the board has been cleaned and dried, insert component from the component side. So we insert the component from the component side. So basically, for a PCB, okay, there will be the component side and also the traces side. Okay, let's say the component side is the top side, the bottom side should be the traces area, the traces side. So we want to put the component, we have to make sure that we put the component from the component side. And then be sure to watch the component orientation, like has been explained before. You want to make sure that the polarity of the component is correct. And then those with polarity and the designated leads configuration might be in the correct direction. So for example, the diode, it has the polarity, positive, negative, plus, minus. So we want to make sure that when we insert the component like diode, make sure that the polarity is correct. Okay. Otherwise, your circuit will not functioning. And then when we do the insertion of the component, okay, once we insert the component, like once I insert this resistor, okay, this resistor here, we should do bending of these leads for about 30-degree angle. Okay, for example, let me just try to draw this. Is it still available? Retry. Power on. For example, if I have the PCB board, so this is my PCB board. So at the bottom, this is the traces area, which is at the bottom side, which is my traces. This is component side. So when I place my component, okay, for example, I want to place the component like the capacitor here. At the bottom side, I should bend it for about 30-degree. Okay, to bend it, this leads about 30-degree before we do the soldering. Not to bend it too close to the surface of the bottom, something like this. So this is not good, because at least we want to allow some space to do the soldering of this pad, of the pad. We have the copper pad. For example, this is our copper pad and this is our leads. So we want to solder it securely like this. Okay, so just at least 30-degree of bending. Okay, when we flip the PCB, it will not drop. Just at least make sure that it is 30-degree bending from the bottom, something like this. So next, component insertion and soldering. So during the soldering process, apply heat to both the component leads and also the copper pad. Okay, so not only apply the solder tip, soldering iron tip to the component lead, but also to the copper pad. Make sure we apply heat to both component lead and copper pad, and make sure that it is enough heat. Don't apply too much heat, meaning that we want to make sure that we do not spoil the copper pad. if we apply too much heat to the copper pad, in some situation it might be rise up, which is floating. So we don't want to spoil our copper pad. So make sure that we apply heat just nice to the component lid and also the copper pad. Okay, sometimes we can use the heat sink device. For example, we can use the needle nose plier, the long nose just now. We just put some rubber band to make it stick, to make it clip the component lid properly. All right. Some tools that we can use, some things like this, which is, it looks like a crocodile clip, yeah, to clip the lid before we do the soldering. Okay, so the function of these tools like crocodile clip here is to divert some heat. Okay, to make sure that there is no excessive heat is given to the lid, so that it will straightly go to the component. Okay, so we don't want to transfer excessive heat to the component, so we can divert some heat using this tool, which is some things like the crocodile clip here. So we clip the component, which is, as you can see in this figure, we clip at the component side. We turn it to the back side to do the soldering process. And then 5.2 is about the design, which is the design phase, which is about cabinet. Okay, so once we finish soldering the components, all of the components on our PCB board, okay, so what we are going to do next is to design the cabinet, which is the enclosure of the PCB board. All right, so why do we need this sort of a cabinet? Okay, we want to make sure we can protect our PCB board. Okay, that is the first thing. So, and then we want to make sure that uh, how do our prototype looks like from outside. Okay, for example, if we want to make a line follower robot, of course we want to design the cabinet of the line follower robot is something like the line follower robot lah, right? So we want to make sure that it looks nice from outside. So that is some of the function of the cabinet. So we have to design the cabinet, not just doing it, not just directly do it from the sheet metal, but we have to follow some of the procedures before we prepare the cabinet. For example, we will start with preparing the drawings of the cabinet. Okay, so some design considerations when we do the cabinet design. For example, the first one is related to the material of the sheet metal. Okay, the sheet metal most commonly used material is aluminum. Okay, we use aluminum sheet metal to do the design of the cabinet. Okay, so some material like cold rolled steel. Okay, sometimes we use some other types of material, but the most suitable material is aluminum. Okay, so the second one is plastic. We can use also plastic, but if we want to consider in terms of safety, we can use plastic. Okay, or wood. Okay, in terms of appearance, wood is much more better. Okay, but we rarely use plastic or wood. Okay, because both plastic and wood, it is expensive. They are expensive. Plastic and wood quite expensive compared to aluminum, and it is also difficult to bend. Okay, difficult to work with plastic or wood. Sometimes we want it looks like some things like luxury. For example, some of the luxury cars, they use wood as a material, right? In terms of appearance, it's good, but in terms of practicality in doing work using plastic or wood, is quite difficult, right? So basically, when we consider doing the cabinet for our electrical device, electrical design or electronic PCB, we will consider using the material of aluminium, okay, which is aluminium sheet metal. This is much more suitable. In terms of size and shape, it depends, okay? So basically, we want to design exactly a fit size to our PCB board, right? So the cabinet should be no longer than necessary to house and mount the electronic. Yet consideration must be also be given to such factors as access to the component part, heat dissipation, project handling. So basically, in terms of shape and size, we are not only consider in terms of size of the circuit board, but also we should consider in terms of heat dissipation, in terms of project handling. Sometimes we want to make sure that when our project is broken, it is easy for us to do the repair or troubleshooting of the circuit board. Okay, sometimes you want to make sure that it is easy for us to assemble and disassemble, to access all of the components. For example, when it comes time to change the component because of it is broken, for example, we want to make sure that the cabinet or the enclosure is easy to be disassembled. Okay, not only just for the appearance, but also in terms of functionality. Okay, ease of repair and also fabrication. Okay, another design consideration in terms of ease of fabrication. At least we want to keep it simple. It's simple design, okay, that sort of philosophy. But sometimes if we make too much holes, too much line for cutting and bending, it is not practical. Okay, so too many bends may simply impossible to achieve. Okay, so make sure that our design is simple enough to make sure it functions well. All right, so that one is in terms of ease of fabrication. And then finally about safety. Okay, we should consider in terms of safety, not only to protect our PCB board or component on the PCB board, but also to protect ourselves. We want to make sure that when we do the repair or when we do the troubleshooting of the component, for example, we want to protect us from electric shock. Okay, and then of course we want to protect our electronic components on the board to make sure that it will not burn out. Okay, in terms of that one is in terms of safety. Okay, some of the design in terms of safety, the components should have some ventilation, like as mentioned in our previous in the previous slides, that some components should have some space for ventilation. Okay, some space for ventilation. Like as you can see for the CPU, computer CPU, it has some fans, right, at the back and sometimes at the top of the CPU, computer CPU, to make some ventilation for the air to cross. Okay, so a good ventilation will make sure that our device or our project or our prototype is always cool when it comes to, because for example, if we use CPU or if we use the solid state device, the hard disk, for example, we can feel that some heat when we touch the hard disk when it is operating. So we want to get rid of all of those heat to make sure that our components always cool down. Okay, our uh, PCB boards always cool down, right? Next is in terms of appearance. So in terms of appearance, okay, we want our cabinet, we want our design of the cabinet to be visually appealing. Okay, in terms of not only the size and shape, the auto finish also contribute to the look of our project, for example. So from the outside, we want to make sure that it looks nice. For example, we want to apply some paint or vinyl coating, for example. Okay. Some consideration in terms of labeling is also important. When we are working on a big project, like that project, for example, project that have some wires, input and output, we have to make labels on that. The line, for example, 5-volt level, 12-volt level, it's different. Grounding grounding level, 5-volt level, 3-volt level, for example. So in terms of labeling, it is important when we do the troubleshooting or when we do repair of the machine, for example, of the prototype, the system. Okay, it should have some labeling. Okay, so the labeling must be durable. Okay, so we want to make sure when we do the label, it is durable. It can withstand, it is not fade out. Okay, it's not fade out, it can withstand for a long period of time. All right, and finally, in terms of cost, okay, the cost is normally something that is secondary consideration, not a primary consideration. Because when we do the prototype, the most important thing is about functionality of our project. All right, so the first thing we are going to consider is in terms of whether or not the project or the prototype that we built is functioning or not. And then cost is secondary consideration. But sometimes when we talk about the mass produced product, okay, we are going to make a mass production of the prototype. Of course, in that case, we will consider the cost as primary consideration. Okay. So 5.2, we are still in the design phase, which is now, it's about the stages that we'll need to follow in the design and fabrication of the sheet metal cabinets. Okay, there are 4 stages that we will need to follow. The first one is to make a design drawing. Okay, the first stage is making the design drawing. And then the next stage is the sheet metal pattern is cut out and holes are drilled or punched in it, making we cut the sheet metal and then making some holes by using drilling or punching. Okay, and then once we finish cutting and making holes, next step is to form the cabinet into shape, to fold it, to fold the cabinet to make it a shape. Yeah. And then finally the surface finish, which is once we finish make the cabinet into the shape, we want to apply some paint, vinyl coating, okay, to make sure that it looks nice from outside, and also to protect the metal, because to protect metal from rust, right? Okay, the first procedure The first stage is sheet metal drawing. Okay, so the sheet metal drawing is one of the drawing available in the 10 set of drawing that we have learned in the second topic. So sheet metal drawing is one of them. Basically, for the sheet metal drawing, it is made full scale, meaning that one-to-one juga. Okay, so full scale means that if we want to make something like a box, which is the dimension is about 10 centimeters, 10 centimeters height, 10 centimeters long, and 10 centimeters width. Okay, so the drawing also must be in the exact dimension, which is 10 times 10 times 10 and times 10. All right, so that is meaning by the full scale. Okay, and then basically the view of the drawing is from inside, which is inside or bottom of the cabinet. Okay, and then from that inside or bottom of the cabinet, then we can fold up. Okay, fold up to the drafter. So basically okay, for example, in this figure, so the view is from the bottom of the cabinet. This is the bottom of the cabinet, so that we have some lines on the right hand side and the left hand side, so that we can fold it. Okay, so this is an example view of the sheet metal drawing. So fold lines are indicated by dotted lines, as you can see here. The dotted lines here represents the fold line, so we can fold from here. Okay, this is the fold line. And then relief holes. So what is the purpose of relief hole, which is something like this? At the corner, we have to make some relief hole, something like this, to prevent bulging and also fracturing. Okay, we want to prevent when we do the folding process. When we fold it, we want to make sure that there is no bulging or fracturing of the edge of the corner of this cabinet. The hole size are given in diameter. So as you can see, for example, there are some holes here. This is the hole. There is no hole size. So basically, the hole size is given in diameter, not the radius. Okay, so hole size is given in the diameter, and when a rectangular shape, the size is given in terms of width time length of the dimension. Okay, and then holes are usually located on the center from a sheet metal edge or fold lines. And then material size types are specified for the sheet metal drawing, and then cabinet finish is stated. For example, as you can see, the material is stated here. As you can see, some things like notes here. So in this sheet metal drawing, the material which is 3003H14, which is the type of aluminum sheet. The gauge here, which is 16 here, is basically the thickness of the sheet metal, which is not millimeter. I think let me just show you the gauge, which is the thickness, something like this. For example, the 16 gauge means about 1.3 millimeter of thickness. Okay, 1.3 millimeter of thickness for 16 gauge. It has a range of gauge from 8 to 20 in this case. So when we choose the thickness of the our sheet metal, the aluminum sheet metal, we should look at the guideline, which is the notes here. This sheet metal drawing suggests that we should use a 16 size of gauge, okay, the thickness, in terms of thickness of the sheet metal. And then the finishing, which is paint flat color, which is white, okay, so white color, and it is paint, not a vinyl coating but paint, in this case. All right, okay, so it's still about a sheet metal drawing. So basically, a complete sheet metal drawing gives enough information to fabricate and surface finish the cabinet. So as you can see in this sheet metal drawing, it does not only give some guideline or procedure on how to fabricate the sheet metal, the cabinet, but also the finishing, okay, in terms of finishing or the surface finish. Okay, with the sheet metal drawing, okay, we can produce a sheet metal template. Okay, so from the sheet metal drawing, which is this, from the sheet metal drawing here, we can create a sheet metal template, which is this template is we are going to use to tape it on the sheet metal, the aluminum sheet metal, as a guide for cutting or drilling and punching and folding of the box. Okay, so it is like something that we can stick on our sheet metal to do as a guide for us to do to make holes, to do bending of the sheet metal. All right, so for the sheet metal layout template, okay, so we can do the photocopy of the sheet metal drawing. Basically, we have this sheet metal drawing. We make a copy of this sheet metal drawing. We make a copy of that sheet metal drawing, and then we cut it. We cut that sheet metal drawing, and then we make it as a template. Okay, what we do is we can use the double-sided adhesive tape to stick that sheet metal drawing on our sheet metal. Okay, sheet metal material like aluminum, right? So when we cut the template, make sure that we leave some space. All of the borders, for example, we have the borders here, the outside borders. We will leave some space about 1.5 centimeter, which is about 1 inch. Okay, to make sure that when we cut this template, when we cut this sheet metal drawing to make it a template, we will cut it for about 1 inch from the border. All right, 1 inch from the border, and then stick it using the double-sided adhesive tape and stick it on the sheet metal surface. This is an example of the sheet metal layout template. Okay, it has some holes, okay, drilling holes, for example, the dotted lines here for bending purpose. This is another hole, ½ inch of diameter of this hole, right? Everything is stated here, like the material also is stated in this drawing. Okay, so this is part 1 of the prototyping part 2. Okay, we still have another slide, which is about cabinet fabrication of the cabinet, which is this one. So now 6:23, we still have some about more than 30 minutes. I think I would like to continue just a little bit. Maybe we will finish up to some slides. This is 5.3, which is maybe we will finish 5.3, okay? And then we will continue 5.4 next week. which is only some few slides from 5.4 combined with topic 6. Okay, so this is the second part of prototyping part 2 topic 5, which is this part will cover 5.3, which is about cabinet the fabrication process, and also 5.4 cabinet the finishing process. Before I begin this, let me just give you some 5 minutes break. So we will start again at around 6:30. Okay, we will start again around 6:30 to complete 5.3. Okay. Okay, let's continue to 5.3. We're still in the cabinet, which is, I'm still talking about the cabinet, but now it's more to the fabrication process of the cabinet. The 5.21 was related to the design phase, right? Slideshow, automatic monitor, automatic primary monitor, record presentation. Where is the setting for auto slides? Auto slide. Where is the setting for auto slide? Custom slide. Use timing. Okay, no timing. All right. So now it's about 5.3. It's still about cabinet, which is the fabrication process of the cabinet. Are you guys still there? How many person now? Okay, still 21 participants. I'm not sure whether you are there or not, but we have 21 participants. All right. Okay. All right. So now we are going to do the fabrication process of the sheet metal, the cabinet. All right. So one we've done with the producing the template, which is the sheet metal layout template, which is something that looks like this. We stick on this template to our sheet metal, which is the aluminum material at the back there. So we stick on this so that it can be as a guide for us to do the folding process, the cutting process, the punching of the holes, drilling of the holes, and so on. So when we cut this sheet metal template, we want to make sure that some blank should be left, should be extend over the template, about 1 inch. Okay, about an inch, about 1.5 centimeter. We leave some blank. Okay, before we cut. And then we can use some tools for cutting, which is, for example, in this case, as you can see, this guy is using what we call as the foot operated squaring shear. This is the foot operated squaring shear. And then another way of using to cut this sheet metal is by using the handheld thin snip like this. So this is the handheld thin snip that normally sold at the hardware store. So this one is more to a machine that is used in industry or used in the factory, which is you in the factory they use this sort of machine to the cutting of the sheet metal. All right. So so we are still in this type of machine. This is this sort of machine which is squaring shear. Okay, foot operated squaring shear, which is the machine like this that is used for cutting of our sheet metal. As you can see, it has a ridge bottom blade, which is this one. This is a ridge bottom blade, and also movable top blade. The top blade is movable. The bottom blade is something like fixed bottom blade, but movable top blade. So there are two blades, all right, here, and then we can use our foot to push this down. We use our foot to push this down to cut our sheet metal. Okay, so something like that. So this is another machine, squaring shear, which is almost the same machine like this, but this one is much more. I think this is bigger size of the shear, the foot squaring shear. So we use that foot squaring shear to cut finely our sheet metal. We can also use the thin snip, but the purpose of thin snip basically for the small project we can use the thin snip. Okay, So this is the way we can use the thin snip to cut the sheet metal. So for the thin snip, basically we can use it for cutting the notch and corners. Okay. Sometimes we can use the more expensive tool like hand operated notching machine. Okay. So basically for a simple project, we can just use this thin snip to cut the notch and corners. All right. And then compound shears, something like this, which is the aircraft type of shears. I have this at home. Some things like this one. I have the brand Stanley brand, which is quite good for cutting the sheet metal. Okay, the aluminum sheet metal. So sometimes we have the compound shell, which is the curve type to make curve, which is the right curve for this one, the left curve as well, and this one is the straight lines. Okay, depending on the application, sometimes we can use this sort of thin snip. Okay, sometimes we can use this type of compound shears like this. And then to make holes, if we want to make a small holes, we can just use the drilling. Okay, we can use drill, whether the drilling machine or the normal hand drill. Okay, we can use the drill for making the holes on the sheet metal. Otherwise, if for the larger holes, we can use the punching. Okay, so basically, for the holes up to 1/4 inch, which is about 1.5 centimeter, we normally can use the drilling. For the larger holes diameter, which is larger than 1.5 centimeter diameter, for that kind of hole, normally we can use the punching, which is punching tools. Where is the punching tools? This is the punching tools, which is the chassis punch. Okay, so this is how we can use the chassis punch. Right, so just go back to the previous slides. All right, up to here. Okay, so this is the procedure on how we can make hole on a sheet metal. Okay, this is about the drilling procedure. So before we can do the drilling process, there is some procedure that we need to follow, which is we use the center punch. Okay, firstly we use the center punch and hammer to make a small indentation and the center of the hole to be drilled. We make something like a home for the drilling. All right, we use the some things like, which is in the figure like this, which is this one is the center punch. Okay, and then use the hammer to make some spot for drilling. Okay, so we use the hammer, just one light tap, to make a mark. Okay, to make a mark, something like to make a mark, to make sure that when we do the drilling, the drill bit at the edge of the drill bit will be fixed. All right, so the purpose of the indentation is to provide a home for the drill bit to prevent it from walking. All right, so to make sure that when we do the drilling, it is safely drilled without any walking. Okay, to prevent the drill bit from walking away from the area that we are going to make hole. Right, so second procedure is we use the backup the sheet metal with a piece of wood. Okay, so we place our sheet metal, and then at the bottom our sheet metal we place some wood, because when we do the drilling, okay, we want to make the hole through. Okay, make the hole which is until the drill bit goes to the back side of our sheet metal. So we want to prevent our drill bit to be broken. So we want to avoid our drill bit to be broken. We make some surface, which is to provide a solid surface for drill bit to enter after it penetrates the sheet metal. Okay, and then also the purpose of using a wood, a piece of wood at the bottom of the sheet metal is to reduce the severity in terms of burrs. To reduce the severity of the burrs. Burrs means there is a figure of burrs. Okay, this one. So this is burrs. Okay, which is some sort of sharp edge after we make hole. After we make hole using the drill bits, there are some remaining piece of metal, which is burrs, something like this. So if we use a piece of wood at the bottom, we can reduce the severity of burrs. Okay, and then fasten the sheet metal and wood backing securely to drill press table, preferable with C-clamp. So we use the C-clamp to fasten our sheet metal before we do the drilling process. Okay, some of the work use this sort of drilling machine like this, which is drilling press table, and then we can also use the handheld drill like this. Okay, so basically we want to fix our sheet metal by using the C-clamp. When we do the drilling, it will not it will fix. It will not. Okay, so drill the hole. Next is drill the hole using appropriate drilling speed and feed. Okay, most of when we make the hole, for the smaller size of hole, basically we can use driller higher driller speed. Okay, but for the larger hole, basically we should use lower speed of the driller. Okay, lower speed of the driller for the larger holes. And then the speed should always be slow, steady pace, and extend at least 1/4 inch into the wood backing, which is about 1.5 centimeter. Sorry, 1.5 mil. Stated here, 1.5 centimeter extend. When we do the drilling, we make a hole. The drill bit, the edge of the drill bit should extend about 1.5 centimeter into the wood backing. Okay. If holes need to be enlarged slightly, we use tapered hand reamer. So this is the figure of tapered hand reamer that is used to enlarge the hole. Okay. Sometimes we don't have the exact size of the drill bits. Okay. So we use the smaller size of drill bits, and then after we finish drilling the hole, we use this tapered hand reamer to enlarge the hole, right? So this is burrs. Okay, the other side of the sheet metal. Okay, at the back of the sheet metal, we usually see this sort of burrs. Okay, this sharp jack protrusion of burrs must be removed. We have to remove this. Okay, how do we remove this? Sometimes we can use the larger drill bit, which is something like in this figure. We use the larger drill bit to remove these burrs. And in some situation also we can use this sort of tool, which is using the Dremel motor tool. This is an example of the Dremel motor tool to remove the burrs, all right? And then we can do it manually using the round nose file, okay? Something like this. But this one is still using the machine like this. This is another shape of bit that is the file, the file that is used to remove the burr using the Dremel motor tool. But also we can use the, there is no figure here. We can use the conventional method of file. Okay, we can use it manually to remove the burr using the hand file. All right. Let me just. We still have some 15 minutes. File round nose file is something like this. We can use this sort of file to remove the excessive burrs. This is another example of the figure or the file that we can use to remove the burrs at the holes. Okay, file ni in bahasa we call it as kiki, right? So next, chassis punch. For the hole which is the size is less, which is the size is less than 1.5 centimeter, which is smaller size hole, we use drilling. All right. But for the hole which is greater than 1.5 centimeter, okay, we can use this sort of chassis punch. Okay, for the holes larger than 1/4 inch or 1.5 centimeter, we use the chassis punch. So using the chassis punch has advantage in terms of burr free. So we use chassis punch to make a clean hole. Okay, the burr free hole, which is the tool of chassis punch is something like this. Okay, this is an example figure of the chassis punch, right? And the chassis punch comes in many size, which is some 3/8 inch to more than 2 inch in diameter. Okay, so more than 2 inch is quite big. For example, my thumb is, I think my thumb is not, the size of my thumb is not, is 1/2 inch, I guess. Okay, maybe about 1/2 inch. But the chassis punch size can go up to 2 inch. All right. So 2 inch is quite big. I think around this size. Okay. And then the chassis punch here consists of 3 parts, which is punch, die, and draw screw. Okay, as you can see, this is punch, this is die, and this screw is the draw screw, right? And then some another way of making holes other than chassis punch, we can use the turret punch. So turret punch also similar to the chassis punch. Turret punch also have different size and punch combinations. Turret punch is much more used in the industry, which is to make a more proper, which is machine. Turret punch is actually the machine that can make proper holes, right? So in terms of for professional hole making tools, we use the turret punch. All right, and then making the rectangular holes and slots. The rectangular holes, we can use the nifty handheld miniature like this, which is this tool is called the nibbler. Okay, we use the nibbler to make rectangular holes. All right. And then finishing up So before the sheet metal can be formed or bent, it should be smooth along its external and internal edge with file. Okay, we can use this file. There are different types and size of files, as you can see in this figure. Different shape and size of the files we can use for finishing of our cabinets. Okay, for example, you want to make the edge of this cabinet smooth. All right, we use the file, we do it manually. Okay, and sometimes you can use the single or double cut file. Some file it has the wooden or plastic handle, which is this one is plastic handle file. All right. So we use the file to prevent the metal particles from clogging. All right. So we still have still have many slides to finish, but we have some 9 minutes. I think I should stop now. Just few more slides. All right. So now we want to forming the sheet metal cabinet. Okay, we want to bend it. Okay, we use this sort of machine to bend our sheet metal, which is the bending brake. Okay, this is the bending brake that is used to bend our sheet metal. So we place our sheet metal here. We place our sheet metal between the fingers of the bending table. Okay, so we move the bending movable bending wing is rotated. The movable bending wings is rotated against a portion of the metal, causing it to bend. All right, as you can see in this figure. Where is the figure? So this is the figure of bending brake. So we place our sheet metal here, and then this is the finger, and then the bottom is the work table, and there's another part which is called as bending wing. So we place this, and then we hold this clamping handle. Okay, pull this clamping handle. Then when it is fixed like this, then we can bend this using the bending wing. I think I will explain this later more on in the next session, I guess. So I should finish now. Finish session now because we are approaching 7. So in our next meeting, we will I will start it from here, which is the finishing up from here, from this slide. Okay, in our next session, I will start from this slides onwards. All right, which is forming the sheet metal cabinet. So for this session, I should finish it up to this time, which is now 6:54. So is there any question? If there is no questions, anytime if you have question, just let me know. Just text me through WhatsApp. Okay. There is one group still not picking up the stuff, the components. So I hope that group can text me or WhatsApp me so that we can arrange a meeting. We can arrange a time, suitable time to pick up. Okay, maybe tomorrow. All right. So I think that's all. So if there is no question, okay, we finish up to this time. Okay. Thank you. I'm gonna stop this. Stop recordings.
Yes, Doctor.
Okay, thank you. Stop.